tell you when we're live.
Facts.
All right, and we are live. So, hello to everyone who's on. Looks like so far we've got one viewer, so hello to our fellow viewer. I have with me today Hamzah, who is a friend of mine from grad school, and he's getting his master's in statistics, but got his undergrad in math. And this is a little bit of a different kind of format here today. Normally, I interview people, find out a little bit more about them. But today we're doing more of a dive into a topic, and that is the Riemann Hypothesis. So we have a lot of cool things to talk about related to that. But before we do that, Hamza, why don't you introduce yourself, tell everyone about yourself a little bit, and then we'll get on into it.
All right. So I am Hamza. I am 23 years old. I am in the statistics master's program at Northern Arizona University, which is where I met Paul. My undergraduate degree was in math from Rowan University in New Jersey. And I did research related to the zeta function and the Riemann hypothesis during my undergraduate years. And so I thought it would be cool to do a video with Paul and sort of explain the connection between the Riemann hypothesis, prime numbers, applications of how these things work, and so on.
Yeah, and so Hamza and we got in this nerdy conversation a while back, and he gave me this book. Can
Excellent
you
book.
can you see it on there? Yeah, this is the book he gave
Hmm.
me a while ago, and about prime numbers and the Riemann hypothesis. So I haven't read the whole thing, but I kind of browsed it, and yeah, and
You
it's
know what?
it's
In that book, only the first chapter is good, basically.
oh, only
Like
the first
after
chapter.
that, only the first chapter is good because it really like nails it. But
Yeah,
then after that, it's kind of maybe the first two chapters. But I know the third and fourth, there should be four chapters in there, and the third and fourth are like not so well put together.
yeah. Let's see. It's a pretty short book actually.
Yeah.
It's yeah. Um, but yeah. Anyway, so we wanted to kind of because I had heard about the Riemann hypothesis in school a little bit. Um, we talked about it very briefly in number theory, but didn't really
Mm.
dive into it. So once Hamza started talking about it, I became interested. We're like, oh, we should do a YouTube on it.
Yeah.
Um, so anyway, let's just start off with like what is the Riemann hypothesis? Like explain to anyone who doesn't. I'm sure we have some people who know about it, some who don't. But let's just back up, kind of give an overview of what it is and why people should care about it.
Okay, so I'm going to start off by talking about prime numbers in general, and without getting too deep into the Riemann hypothesis and like this beginning of the video, I'm just going to say like I'm just sort of going to explain how the Riemann hypothesis is like vaguely related to them.
Yep.
So prime numbers are positive numbers that are, well, I guess by definition greater than one, that are only divisible by themselves and one. And so like you can look at 2, 3, 5, 7, 11, and so on, and there's infinitely many of them. Now, one is not prime. Why is one not prime? Paul, what do you think?
You know, this is an interesting question because by definition, the primes start at 2, and the only
Yeah.
even prime is 2, and 1 is divisible by itself and 1 because it's 1.
Yeah.
Um, but to me, I always thought it was just by definition. So I'm not actually sure on that.
Yeah. So a good reason for it is the fundamental theorem of arithmetic, which says that every positive number is either prime or can be represented as a product of primes uniquely, right? Up to a permutation. Like for six, it's two times, we know it as two times three,
Yep.
but you can also write it as three times two. You can reorder them, but it's still unique. Now, what would happen if one is prime? Then six is not just two times three, it's one to the n times two times three, and n could literally be anything.
Oh yeah, that's a good point. Yeah.
So then you would
So
be
then
able
it
to
wouldn't
factor
you wouldn't
numbers.
have a unique factorization for every number. Yeah.
Exactly.
Because
You
then
would
you
be
could
able
do
to,
1 squared times whatever the other prime
yeah.
factorization is, 1 cubed, 1 to the fourth.
So it would be, there would be infinitely many ways to factor numbers.
Yep.
right? Which would be crazy. So I think that's probably a good reason for it. But again, like you said, by definition, they just start at 2. But I think that the fundamental theorem of arithmetic is probably a good reason for it.
Yeah.
Now, these prime numbers, the cool thing about them is there's no pattern to these primes. Like you can say 2, 3, 5, 7, 11, 13. Can you predict the next prime? And the answer is no, without actually testing each number. However, prime numbers do tend to behave in a certain way. So as you approach infinity, these prime numbers tend to become more scarce. Like they're like they become way more spread out, right? Mm-hmm. So now the Riemann hypothesis is this conjecture that the Riemann zeta function, which is a complex valued function, has its zeros only at the negative even integers, which are called the trivial zeros, and on the critical line where the real part of your input is 1/2. And these are called the non-trivial zeros. Now, the real point of this Riemann hypothesis is really the non-trivial zeros. Like you'll never hear people talk about the trivial zeros because it's like they're trivial. So the connection between them at first glance is in number theory, the Riemann hypothesis is equivalent to a lot of nice statements, I guess you can put it. Like there are so many theorems that go like, if the Riemann hypothesis is true, then blah, blah, blah.
Right.
Like a lot of them. And you can kind of summarize all of them by just saying that these prime numbers are distributed in like the nicest way that you could imagine. Like they're distributed very, very nicely. So it's mostly about the distribution of these numbers. And let's say, how do I put it? So there are very good approximations for the density of primes. So how many primes exist less than a given number? There are very good approximations for that. If the Riemann hypothesis is true, what it would do is it would guarantee a bound for the difference between this approximation and the real value and the true value of how many primes are less than a given number. So you know that you'll always, if it's true, you'll always know that you're at least within a given range, always.
And didn't you say that error bound is within the square root of the number that you're after, or was that related to something else? Yeah.
No, yeah, that's completely right. Yeah. So it in the prime number theorem, which we'll get to, but we can talk about now. Actually, the simplest way to put it is if you look at any interval that's a little bit bigger than x to the half in length, the Riemann hypothesis would say that interval contains primes. So any interval from x to x plus x to the 1/2 plus some positive epsilon.
For example, if I chose 100, we would say between 100 and 110, because 10 is the square root of 100. You're saying there exists at least one prime between 100 and 110.
Yes.
Did I state that correctly?
Yeah. So I think, what would that be? I think 103 is a prime?
103, yeah.
Yeah. So every such interval would contain primes if the Riemann hypothesis is true. Though not to get into too much detail, but I've also read that for that kind of conclusion, you actually may not need something as powerful as the Riemann hypothesis. Like if there are a couple zeros that are off the line, as far as there's not too many of them, you can still get a lot of these conclusions. Interesting. Okay. But yeah, but if we're just focusing on the Riemann hypothesis, that's one implication of it.
Yeah.
Yeah.
That's interesting. So we're basically the whole goal of this is we're trying to count how many prime numbers, which basically we could say are like the building blocks of numbers. So how many building blocks are there that are less than a given number? And so we're kind of saying how sparse or dense is our neighborhood of building blocks in a way, I guess would be another way to put it.
That's a very good way to put
Something like that.
Yeah.
And the Riemann hypothesis is telling us that Riemann believed there was a direct way to count those. And you're going to talk about like approximations to that. Am I stating that right, or am I off?
Yeah. So we'll get to what the zeros imply, and we'll refer to them later in the video as correction terms. So you basically start with an initial approximation, and then you use these zeros to sort of get you closer to this real answer, and it only holds if all the zeros are with real part 1/2. Because
Okay.
if you have a zero that's off the line, then pretty much all of it gets ruined.
Yep.
In a way, yeah. So, so what should we talk about next?
So, well, I wanted to ask you about like implications and applications related to this, but if you had anything else you wanted to talk about related, or we could move on to that topic now.
Well, for the Riemann hypothesis, I actually just wanted to keep it at that
Okay.
before we move on, because we'll actually get into it after we do like applications. I actually wanted to show like a graph of how these zeros work. So I think that would be a good time to do it.
All right. So let's do that
end.
then. The implications, applications, maybe why people should care about this. I know you kind of alluded to that already a little bit.
Yeah. So, well, implications. So if we just talk about pure math, so in number theory, the Riemann hypothesis being true would sort of like validate a lot of these statements, right? Which again we'll get to, like sharp estimates on the error term in the prime number theorem. That would be like a consequence of the Riemann hypothesis being true. Now, in the field of number theory, there are a lot of ways that you can relate the Riemann hypothesis to prime numbers, like because of all these theorems. Like you can say that's what it implies, or this, or this, or this. And only people who specialize in number theory can sort of get to dive deep into this and really gain a deep understanding.
Yeah.
But for people like you and me, we just want to like sort of look at it and say, okay, that's the idea. That's what these zeros are doing. That's the connection. It makes sense.
Right.
Without necessarily going like way, way deep into it. Now, I've actually talked about this with you before. So an application of not necessarily the Riemann hypothesis, but prime numbers in general, like we talked about RSA.
Yep.
And I've thought about this, and again, we actually talked about it when you talk to someone about like who knows about the Riemann hypothesis and stuff like that. They'll say something like, "Oh, if it's true, then RSA would be broken. Like it would blow up the entire system." And I disagreed with this, and I actually told you this because, like, in my head when I was thinking about it,
And
I'm like,
actually,
okay,
just for our viewers, can you give a quick description of what RSA is and what that stands
I
for?
probably should do that. Yeah. So RSA is RSA are initials of people that came up with this encryption method. And what RSA basically is if you think about how you can send a message to someone or an email to someone or like DM someone on Instagram without anyone else reading it, there are encryption methods that are in place.
Yep.
One of which is RSA, which mainly takes advantage of prime numbers. And so that's sort of the idea of what RSA is. But to get back to what I was saying, I told you that I disagreed with this, that the Riemann hypothesis probably wouldn't break RSA, because if I'm thinking about it, I'm like, why can't someone just assume that the Riemann hypothesis is true and then use it to break RSA? Like, wouldn't that sort of make sense? But then I thought about it some more, and I'm like, okay, maybe the idea is like whoever proves the Riemann hypothesis in the process would make some like profound discovery about the distribution of primes that maybe makes factoring that much easier, which would then be a threat to RSA because
then you could find the key a lot easier that way.
The private key, yeah, you can decrypt messages, because what does the security of RSA rely on? It's the difficulty of factoring prime numbers.
Yep.
Or not factoring prime numbers, factoring numbers, composite numbers.
Factoring numbers into the two primes that were chosen to create it.
Into the two primes, yeah. So the security of the whole RSA encryption depends on the fact that you cannot factor numbers easy, like time complexity wise. Like if you try to get a computer to factor larger and larger numbers, there will be like a runaway effect. Like eventually it'll take like literally hundreds of years for a computer to be able to factor like, I don't know, like a 500 digit number or something.
Yeah.
So there does not exist a method that can factor numbers in polynomial time, a classical method. So by classical, meaning like regular computers that encode information in binary.
And I'm going to stop you for 1 second in terms of polynomial time. For anyone that doesn't know, can you kind of talk about? I know there's like polynomial. What is there? Is it big O? Big O? Am I remembering correctly? Or
yeah, it's big O of n to the k.
Yeah.
So basically, the running time of the algorithm would be bounded by a polynomial on the size of the input. But I mean, for the purposes of like, I can think of sorting algorithms that are polynomial, maybe selection sort.
That might be, but yeah, basically the idea is that polynomial time, it would be a lot faster than other types of things. Just to give everyone, I know some people that are watching probably know about that, but just simply put.
So just summarize it. It's fast.
Yeah.
Right. So there does not exist a method that can factor numbers fast in a classical computer, which encodes information in binary. So, the computers that we use encodes information in zeros or ones. And the whole RSA encryption algorithm takes advantage of that.
Right.
Like if I give you a 600-digit number and I say, if you can factor it, I'll give you $10 billion. I don't have $10 billion and you're not going to factor it.
Right.
Like
exactly.
that's what it is, right? So.
Yeah, you could spend every waking hour of your entire life and you would die and never figure it out.
And even with a computer, I'm not even telling you to do it by hand.
Yeah.
I'm like,
even with
use
the computer.
whatever resources you want. Yeah, like use whatever you want. You're still not going to be able to do it.
Yeah. All right, so on this note, are there any algorithms or anything in place that you think could break this?
So there is an algorithm that can actually do this, and it's a quantum algorithm. But I feel like before we do that, should we explain RSA more?
Let's do that. Let's jump into that.
Maybe, because I feel like maybe we can, actually, I'm going to use a website to sort of, and we'll do like an example of how, if you can factor primes, you can, I don't know how you would hack into the website after factoring it, but you would be able to
somehow once you have those, somehow you'd get in.
Yeah. All right, so you can see the Wolfram Alpha piece?
Yep.
Okay, good. So going back to this RSA algorithm, again, it is used to encrypt and decrypt messages. So it's all about security. How can you send a message to someone without anyone else reading it? And I'd say the answer is prime numbers, but that's only if it's RSA, right?
Yep.
So the reason that I'm using Wolfram Alpha is because they use RSA encryption. There's also the elliptic curve method that's used by like Google, I think. Yeah, Google uses elliptic curve, I believe, excuse me. So whatever website that you are on, you can always get the public key encryption information. Because, the reason that it's public is because you want to use it to encrypt messages.
Yep.
Right? So if you hit, right now I'm using Chrome, but it actually doesn't matter if you're on like Safari or Firefox, it's all the same. If you just hit this like little lock button and you go to certificate and then you hit details, down here you'll see public key information that is available.
Yeah.
Right? So the first thing to notice is the key size. It's 2048 bits. Do you know how many digits that is?
I'm not actually sure.
I mean, if I were to guess, I'd probably say 600 because I know that the number's probably 600 digits.
Yeah, because the number's in hexadecimal, right?
This number, yeah.
Oh, the public key is, yeah.
Yeah. I think it's probably
2048 bits. I don't know how many digits that is.
We'll say 600. I don't know. Or maybe at least 600.
Yep.
So in RSA, there is a public key that you use to encrypt your messages, and then there's a private key to decrypt the message. But the private key is private, right? So the public key comes in a pair, and the pair is this 600-digit number that will actually convert in a sec, and then a public exponent, which is normally set at 65,537. And we'll see how, like we'll basically like do an example in our head.
Yep.
So if I copy this number, and I actually already have this website pulled up.
Are you going to convert it?
Yeah, I'm going to convert it.
Oh, look at this.
Just to try it. So, well, let me reset this for.
You're converting it to base 10?
Yeah, actually, there we go. So if I put this number in and I hit convert, we're going to convert it, to base 10. You get this very large number. Like, look at how long. Like,
so just to give anyone a quick review of how the difference between hexadecimal and base 10. Base 10 is like the common numbers that we look at. So if you take the number like 223, it's 3 times 10 to the 0 plus 2 times 10 to the 1 plus 2 times 10 squared is how you get 223. Hexadecimal, you're using base 16. So instead of digits like 0 to 9, you have digits 0 through F, I believe, because they start using letters. So you have 16 digits, 16 digit / characters, and you're using base 16 as opposed to base 10. Just a quick.
Oh, so it goes 0 to 9, and then it picks up A to F, right?
I think that's right. Yeah, because how many are A, B, C, D, E, F? I got to count on my fingers.
Yeah, so that would make sense.
That would make 16. Yeah.
10,
so 0 to 9 and A to F. So that was just a quick review of base whatever, and then like computers using binary 0 and 1 is just base 2. So
yeah.
So yeah, we're looking at base 16. That's crazy. That's crazy. It could convert it. That it seems kind of fast.
It did. It actually took me because I used the website before it, and it just wouldn't convert it because like this number, if you look at it, it was spaced out, so it didn't recognize that you should like skip these spaces, but this website did.
Okay,
yeah, because I wasn't about to go on every space and hit backspace.
Yeah, seriously.
That would have been a complete waste
you could
of
go
time.
write a program to go delete all your spaces. It would take you a while to write that program, though.
No, actually, I think if you put it in like a text document, you can edit text.
You can actually do it in Excel really quick.
Or like Excel, but you can have it just look for a symbol and delete
it.
Yeah. But anyway, so if you look at this number, like this goes a while, and we shouldn't count this, but it's probably like around 600 digits, I'm thinking.
Probably.
But the idea is, so if we go back to Wolfram and I pull up that information again, what do we have? All right, so let's do an example using this. So what do we have right now? We have this 600 digit number that we just converted, which we don't really need to know what it is. It's just very, very large. And that number's composite, right? And it's the product of two 300-digit prime numbers, I'm assuming, that are unknown. And if you can figure them out, you're rich.
Yep. So this is the number that we are trying to factor into two primes to decode this website. Which I don't know why we'd want to hack into Wolfram Alpha, but hey. If we could do that, we could hack into a lot of other sites.
I mean, yeah. All right, so pick a number, Paul.
All right, any number?
Any number.
301.
301. All right, so let's say that I want to send you a message that's just 301, right?
Okay.
So how would we encrypt this? I would take the 301, I would raise it to this exponent, 65,537, and then I would take it mod this 600-digit number. So
okay.
In normal words,
so are you saying 301 is after my message could be hi Hamzah, and you convert that into a number and then raise it to the exponent?
Yes. Okay. Exactly.
So 301 we'll say represents hi Hamzah. And
we'll say that. Yeah.
And then so raise it to the exponent, then take mod that big number.
Yeah. So in words, let's say it in, maybe you don't know modular arithmetic, you would basically take 301.
By the way, this just reminded me. We can talk about this later, but modular arithmetic, that reminds me of the dream I had that you and I discussed, and you discovered the meaning behind my dream.
We should talk about that at the end.
We should. Well, okay, we'll leave everyone on edge about that. I had a weird dream that Hamzah figured out, so. All right, continue.
All right, so in words, what did we just do? You take 301, you multiply it by itself 65,537 times, and then you would take the remainder when you divide it by the 600-digit number.
Yep.
That's really what modular arithmetic is. You're just always taking the remainder. And that would be the encrypted message.
So, like, for example, we could give them an example of, like, mod 9. So,
Yeah.
like, if I did 11 mod 9, 9 goes into 11 once with remainder 2. So, 11 mod 9 is 2. That's modular arithmetic. Or,
Yeah.
20 mod 9, it goes in, what, twice, remainder 3. So, that's 3.
Yeah, it's also called, I think, clock arithmetic. So like if you basically make a circle and you write 0 through 9 and you want to go 11, then you would just start at 0, go 11 times, and then you'll end up back at 2.
Yep.
That's probably like the easiest way to think about it. But so once you do that, you end up with this encrypted message that, well, you wouldn't get it. You would get the decrypted message. But there is the encrypted message, let's say like, I don't know, 7 or something.
Yeah, whatever it is, we don't know, but
yeah,
can't do that in our heads.
So then there's a private key, right? And the private key also comes in a pair, and the pair is this 600-digit number and a private exponent, D, I think usually they call it. So the idea is if you know what D is, you can reverse this process and get your 301 back, right? The only way that you can figure out D is if you know the factors of this prime number. Now that's where, well, maybe I'll go over it. So that's where what's called Euler's totient function comes in. They call it the phi function.
Euler is involved in everything.
Everything for no reason. He's everywhere.
Just a genius.
For no reason.
For no reason at all.
So this phi function, what it does is it computes the strength of a number, or like the breakability. And what that means is it counts the number of integers less than or equal to n that share no common factor with n. So if we look at phi of 8, what numbers don't share a common factor with 8? That would be 1, 3, 5, and 7.
Oh,
if
because if you chose 2 and 4, those all share a common factor. Wait, so 6? Yeah. Oh, 6 shares a common factor because of 2.
Because of 2, yeah.
Yeah. Okay.
So basically, you want to say they're relatively prime. So their greatest common divisor is 1.
Interesting. Okay. That's relative primes. Yeah.
Yeah. And then so if we look at phi of 9, do another example. That would be 1, 2, 4, 5, 7, and 8. So 6 of them.
Yep.
And you can see that if I give you like
you're counting, the function counts relative primes.
Yeah.
Okay.
Pretty much. And that's called like the strength of that number. So if I give you like 350, like it's hard to compute this phi function.
Right.
Right. But what if the number is prime? What does the phi function give you?
Oh, then that's gonna be a lot easier.
It's literally like if I give you 11. Then there are no, it's co-prime or relatively prime with every number leading up to it. So the number of numbers that share no common factor with that number is just that number minus 1.
Gotcha.
Right? So phi of a prime number p is just p minus 1.
Yeah.
Which is super easy.
So if you're trying so like for 11, then it would be 10 because you're saying it would be 1. Oh, but what about 1? Do you include that?
Well, what's phi of 1? I guess that's just 1, yeah. Because we're
counting. But I mean, like if we were looking at 11 and 20, for example, we're counting.
Oh, you count 1, but you don't count 11.
Okay. So there's 10 then.
Yeah, because the greatest common divisor of any number in 1 is 1.
Yeah.
So
Okay.
I guess are they co-prime? Technically, they're relatively prime, right?
Yeah,
I guess.
I think so. Well, I'm just never sure about 1 because of the fact that 1 is not a prime number, so I'm never sure if by definition they do something weird with 1. But I liked your description at the beginning though about like the unique factorization of numbers. Like I think I had heard that in the past, but I had forgotten about that, and it's a good point. I bet you that's why by definition 1 is not a prime.
I mean, it would make sense because you need them to be unique.
Yeah.
Right.
Exactly.
well, I guess you don't need them. Like, they weren't unique. It's not like we'd be able to do anything about it, but
Yeah.
it's nice if they're unique.
Right.
Right. Yeah. So wait, where was I? Okay. Yeah. So this totient function, right?
Yeah.
So in order to find D, you need to take phi of the first prime times the second prime. And this function is multiplicative. So, I mean, the easiest way to say what multiplicative is if you have phi of A times B, it's the same as if you evaluate them separately and then multiply them. So phi of A times phi of B.
Okay.
That's what multiplicative means. This function is only multiplicative if the numbers are relatively prime. And if you have two primes, then it would be multiplicative. So if you know what these two factors are, you can calculate that phi function, and then you can figure out what D is.
Okay.
So, I mean, if you think about this algorithm, they literally give you everything except the prime factors. Like, they're like, here's everything, just find the prime factors.
So literally, yeah, this whole thing relies on factoring, being able to factor into prime numbers.
Yeah, because, you know, there's no threat today. But there will be probably soon.
And if quantum computing gets to a point where it's fast enough, basically.
Yeah. I mean, I don't know. How long would you give it? Because most quantum computers today, which we'll talk about, how that can be used to break the system. But like quantum computers today, I think operate on not many bits at all.
Yeah.
So I'm not really sure how, because you would think they're already preparing to make a transition to another encryption system, because I think not even an elliptic curve cryptography can stand against quantum computers.
It's crazy. So, quick side question. You don't have to dive deep into it, but the elliptic curve method, is it drastically different from this method?
Yeah, it uses properties of elliptic curves. Like, if you look at the elliptic curve equation, and there's like a whole method that goes into it. It is more efficient. Like, as I said, the key size is always much smaller.
Yeah.
But the level of security is the same, so it's more efficient. But I believe it's harder to implement, and it hasn't been around as long as RSA.
Okay. Yeah.
Because, I mean, RSA is good to go. Like, I guess you don't really need elliptic curves. But yeah, I mean, it requires much smaller key size, so the encryption speed is faster, and the security level is the same.
Right.
But I'm not too sure about this, but I don't think it would be able to hold against quantum computers.
So, I keep having these side questions, but I don't know how much you know about blockchain. Is it fair? I know a lot of it does rely on prime numbers and cryptography similar to this. Are the encryption algorithms kind of similar to this, where you have two really big primes and it relies on factoring the bigger number when they're multiplied?
RSA, that's all it relies on. Elliptic curve, I don't think so much, because it uses like a completely different method.
Elliptic curve, but what about blockchain? Do you know? Does it?
No, I actually don't know.
Not sure
how that works. Yeah,
I don't know much about it honestly either.
Yeah,
I mean, I know it relies on prime numbers, but that's about the extent of my knowledge with blockchain. So
I mean, if something, like a rule of thumb, if something relies on prime numbers, it means that they're depending on the fact that you can't factor them.
Okay. Yeah.
Right, because that would be like the most useful way to exploit prime numbers.
Yeah.
Right.
Yeah.
And prime numbers have a funny thing. Like, people usually don't understand how important, or they don't really realize how important these prime numbers are.
Yeah.
Right. Like, you can say you can send a text to someone because of prime numbers, but I mean, I guess that wouldn't totally be accurate.
Right.
But I mean, it's true. Like,
yeah.
They're very important, right?
They are.
And
I mean,
they have
everything we're using on a daily basis. It's pretty crazy, actually, that basically number theory, which is a pretty advanced math course, is being used by everyone on a daily basis, pretty much.
Without realizing
it.
Yeah. Well, I guess you only need a little bit of number theory to use, because then the rest of it just goes into crazy stuff.
Good point. Yeah.
That,
All right. So I wanted to kind of circle back. We started talking about zeros, and my next question is, how are zeros related to prime numbers? I know you were talking about trivial and non-trivial zeros. If you want to touch on that, unless you had something else on this topic before we move on to that.
So maybe we should talk about quantum computing first and explain, because I actually wanted to explain how you can break RSA using quantum computers.
we barely started talking about that, and then I interrupted you, and I forgot we hadn't finished that topic.
So yeah, let me do that. It shouldn't take long, because I don't really know that much about quantum computers, but it's really fascinating. So there's this algorithm called Shor's algorithm, and it requires a quantum computer that can factor a number n in polynomial time, or fast. It can factor numbers fast. And it does so by taking advantage of what's called superposition. So what I want to do is I want to explain what the idea of what superposition is and how this algorithm takes advantage of it. So if you have a sufficiently large quantum computer, and I say sufficiently large because I don't know how big you need it to be, right? You can break the public key cryptography scheme. Now, because of how the quantum world works, this algorithm is not deterministic. So it'll give you the answer, but with certain probability, like high probability. So there is error involved, but I mean, you can combat this by just like running it a bunch of times, right? And you would just decrease that rate, and you'd be good to go. Right. So that's not really a problem. So this superposition idea, what does it mean? So quantum computers use properties of quantum physics to perform these computations. Like when we think about classical computers, regular computers, they will encode information as zeros or ones, right? In quantum computers, the basic unit of memory is a quantum bit, or they call it a qubit. And these qubits are made of subatomic particles. So they obey subatomic logic. And so each particle is like a smear of probability. Like what that means is in the quantum world, these subatomic bits, they don't follow intuitive logic that you would expect.
Yeah.
Like, from objects that you can see and like hold.
Right.
Each particle, and I don't think it still makes sense to me. So each particle can exist at any given place, or can be found at any given place, but the probability of is probability the right word? We'll just say the probability of you finding.
I like how you call it a smear of probability.
No, like that's what it actually is.
Yeah,
like
it's just
it blows my mind.
So are you saying like the probability of one of these particles being in a certain place at a given time? Is that kind of what?
It's zero. It's zero.
Or extremely small.
Like
basically zero.
Like basically zero is what I meant. Yeah.
But if you add them all together, you get 100%.
I would hope, or maybe not. I don't even I'm not even gonna make that.
Like, are we talking the rules of probability here?
No, like it's really very interesting how it works. But this gives them a certain property. So anyway, information is not stored as zeros or ones. They are stored in and I got this phrase online because my mind is still blown. They are stored as a series of quantum mechanical states. The spin direction of like an electron or something. So what this means is that each particle can be in more than one state at a given time. So each particle can hold more than one bit of information.
Interesting. Okay.
How does that help us? Well, for example, if we think about, let's say you have 8 bits in a classical computer, that would allow you to represent any number between 0 and 255 with 8 bits. If you have 8 quantum bits, you can represent every number between 0 and 255 at the same time. And that's called superposition. So,
interesting.
Right. So if you think about working with a problem where you have many different possibilities, this property would allow you to consider them all simultaneously. Like that's very powerful, which Shor's algorithm takes advantage of, right?
Yep.
So how does this relate back to Shor's algorithm? Well, it consists of 2 parts. The first part turns this factoring problem into a problem of finding the period of a function, which you don't even need a quantum computer for that. You can just do it like normally, classically. I don't know. You don't need a quantum computer for it. But the second part, it evaluates it finds the period of that function by evaluating that function at all points at the same time.
Yep.
Using quantum Fourier transform, which depends on the computer's ability to be in more than one state at a time. So that's what's going to cut down your 10,000 years of computational time down to like not that much time, right?
And we don't know how much that is, but a lot less.
Like way less. Like you can, like in one sitting, you can break RSA. Yeah, it's like using Python to.
So are you saying this is a possibility? Like, because don't they already have quantum computers? Are you just saying quantum computers have to get to this level that you're describing in order to do this?
Yeah, or... they're not powerful enough for this algorithm to be used in a serious way. Like, I believe that I've read some stuff where they actually did they implemented this algorithm to compute like not so large numbers, and it works.
Yeah.
But they don't have. I mean, I guess the way that it would work is you need them to operate on way more than 100 bits, quantum bits.
Okay, gotcha.
For this to be a threat. And
it's so crazy. So what kind of a threat is this to our society then? Like, let's say quantum computers get to that. I mean, I'm sure people are I hope people are thinking about this.
Well, you would hope that these whoever's in charge of these RSA encryption stuff and the elliptic curve are already preparing to make a transition.
Right.
But I mean, also if you think about it, like if a powerful enough computer is made, one, it's probably going to be super, super expensive.
Right.
Or it's only going to be available to people who are trusted.
Right.
Like no one at home is just going to have a powerful quantum computer.
People are going to start passing these things around on the black market.
I mean, it probably eventually, but by that time, you would assume we're so advanced that this thing's like a joke.
Right.
And we start talking about a different computer.
Yeah. That's so crazy.
But I mean, how long would you give it until
quantum computers are at that point? I have no idea, but I know what's the rule of like they say that like at least traditional computers double in speed every it used to be every couple years or there's some rule basically that like.
Well, yeah, but I don't think that would affect like the progression of quantum computers.
Probably that's what I'm saying. Traditional computers, like that's why I have no idea in terms of quantum computers when this would happen. But I'm gonna 20. I was gonna say I'm gonna guess 15.
Yeah, probably 15 to 20 would probably be a safe guess.
Yeah.
But I mean, I think we'll be okay because I'm assuming I'm hoping they already have like a plan to transition us into.
Right.
Yeah.
So do you think there will be a point in time where you and I can own a quantum computer affordably, like in our lifetime?
Probably. If they become, I mean, I guess it would depend on how easily they can make them.
Yeah.
And it's like if they make so many of them that they can just sort of like give some away, sell some away, then I mean, yeah, why not?
Right.
And they would need to make sure that no one can sort of use them in a threatening way.
Yeah.
Because there's superposition, which is like
so crazy.
It's wild.
Yeah.
So I mean, yeah, probably in our lifetime, I'd say so. Hopefully, maybe.
That's wild.
Because this algorithm's been around since like 1990s, I think.
Okay.
Like it's been a while. It's not like something new.
Right.
So, but I'm assuming it was all mostly theoretical at the time.
Yeah.
Yeah.
That's so wild.
So that's good.
All right, so now I wanted to ask you about the zeros.
Yeah. So now the exciting part.
Yeah, the exciting part now.
Okay, did we didn't talk about the logarithmic integral, right?
No, we did not.
Okay, good. So let's start off by this. So if we denote the number of primes less than a given number to be pi of x, so pi of 10...
Where x is the given number.
X is the given number, yeah. So pi of 10 would be 4 because there are 4 primes less than or equal to 10.
2
pi of
5 7. I'm just counting them. 2 does that skip? 2 3 5 7.
Yeah.
Those are the 4.
2 3 5 7. So 4. And then pi of 100 would be 25. There are 25 primes less than or equal to 100.
Yeah.
I don't think you want to count those.
I don't. I'm not going to. I'll
That's
screw up on live video. I already missed
yeah.
three, so.
So pi of x is a step function, and it goes up wherever there's a prime. So the prime number theorem tells us that a very good approximation to this pi of x function is the logarithmic integral, which is the integral from 2 to x the given number that you want to find the number of primes left in,
Yep.
of 1 over log, well, I don't want to say x, 1 over log t or something. So if you evaluate, for example, the integral from 0 or from 2 to 100 of 1 over log t, you'd get something like 29, which is within square root of 25, right? So
it's crazy.
So that's a pretty good approximation, right? You can think of the prime number theorem as saying that the logarithmic integral in pi of x, what are they, like asymptotically equal, or they go to infinity at the same rate or something?
Yep.
Something like that,
I think
right? So
asymptotically equal would be, it sounds like a good way to phrase it.
like that means that their limit equals 1 as you approach infinity.
Yeah.
I think the limit of their quotient. But yeah, so the Riemann hypothesis says a lot about this approximation, which is the logarithmic integral, right? So the way that I want to do this is, let me see if I have it pulled up, but we want to look at Riemann's explicit formula. Let me share. Can you see like the Wikipedia page?
I can, yep.
All right, good. So the formula that we want to look at is this f of x equals whatever. So the first term in here, this is the logarithmic integral, right? So if you plug in x equals 100, this is going to give you 29. And then there are 3 other terms.
The other terms are correction terms, basically, to that initial.
This is the correction term, the second one.
Okay.
So these two, I don't really consider them to be that important, because log 2 is what, like point something, like it's less than 1.
Yeah. Is it, well, if we're doing base E, which
I think it's
I've never
less than 1 for both, I think.
It's what?
I think it's less than 1 for, no, I don't know.
Yeah.
It's small, right? So whatever it is, it's small. And this integral is actually due to the trivial zeros of the Riemann zeta function, which occur at the negative even integers. And this also, this is also very small. I think this is like, I think it approaches 0 as x goes to infinity.
Okay.
So these two terms, like, you can kind of just ignore. Like,
they're
they're not going to do anything for you. Yeah, they won't help you out.
Yeah, I guess from what I was saying, it doesn't even matter if it's base E or base 10. That's still log 2 is still a decimal number. So.
Right. Yeah. So it's still small in magnitude.
Yeah.
So this term right here. So ignore this Li. Like it kind of makes stuff more complicated. Let's ignore it. So if we just look at this sum, this is a sum over all these non-trivial zeros of the Riemann zeta function. So if we assume, before I show that graph that I wanted to show, if we just sort of think about it, if we assume the Riemann hypothesis is true, what does it mean? It says that the real part of each row is 1/2, which would mean that each individual term is of size x to the half. And so you can sort of treat this like an error term or a correction term of size at most x to the half, and you would be able to get a very good approximation to this counting function of prime.
That's why you're saying that the bound is basically given by the square root of whatever the number is.
Basically, yeah. Like this, it's all related to 1/2.
Yeah.
Right? So you can think of this as you start off with an initial approximation, the logarithmic integral, and then the more of these zeros that you add, the closer that you get to the true value. So they adjust your initial approximation.
Yeah.
They keep just adjusting it. Now, what if the Riemann hypothesis is false? Then you'd have a term that, I guess, grows faster than x to the half, and then everything just collapses.
Okay.
And that wouldn't be good. But I mean, the zeros have been numerically verified up to like 10 trillion, I think.
So we'd have to find, would have to find some counter example off somewhere off to infinity.
Yeah. That's I mean, I think for certain fields it's like, because it's been numerically verified for that high, that they can just assume it to be
Assume
true.
it's true. Yeah.
But for math, it's like, you can't assume it's true
Right.
unless you have like a rigorous proof of what's
Yep.
going on.
Yep.
So the simplest way to think of it is you start with an initial approximation, and then you have a bunch of corrections.
Yep.
These zeros contribute a bunch of corrections. So let me move on to this graph and make it full screen. Can you see it in full?
Yep. Sure can.
All right. So this down here, you have the staircase of primes.
So that's
right?
actual. This is just to clarify for everyone. That staircase is counting actual primes.
Yeah. So you can go to like 200, go up, and you'll see that there are 46 primes less than 200, and so on.
Yep.
And so this is it keeps just going up, and this line is obtained from the function that we just looked at, this Riemann's formula.
With k equals
now,
1.
With k equals 1, k representing the number of non-trivial zeros that you have added, or you have included, right? There's infinitely many of them. Right now, we've only included one. So one thing I want to mention about this before, I mean, we don't need to worry about it, but this Riemann counting function, it doesn't only count primes, it also counts prime powers, but it counts them as worth less. So if you're trying to find the number of primes less than or equal to 30, at 3, you would go up by 1. At 3 squared, you would go up by 1/2. And then at 3 cubed, you would go up by 1/3, and so on. So if you have p to the n, it's counted as 1 over n.
Okay.
But, I mean, you can relate it back to pi of x, the pure number of primes within a given number, by using what's called Mobius inversion. But for the purposes of, I guess, this graph, we're just going to ignore that. Like, assume we're just approximating primes.
Yep.
So k is 1, or, I mean, basically 0. Like, we've only included 1, so it doesn't really do anything. So initially, we can think of this line as we obtained it by just the logarithmic integral, that log 2 term, and then the other integral. And what we want to look at is what happens to this, I guess, graph, this line, as we keep adding more and more zeros. So we're going to see what happens. So you'll notice that, I'm going to go pretty fast. Did it just crash?
It crashed.
Oh, man.
Crashing your computer. We saw it like up to 14, and then it disappeared.
Is it back?
Yep.
Okay, it's back. All right. All right, so I'm going to go fast again.
Okay.
And you'll notice that it starts to like swing back and forth.
Ooh, this is
based
crazy.
on, oh my God.
There it goes again.
You gotta be kidding me. Hold on. I think I need to close everything. Let me force quit and then come back, because this is.
I know this graph is super cool to see. So.
All right, so I think it's in my downloads. Do you see prime counting function anywhere?
Yeah, there.
Oh, here it is. All right, excellent. Here we go. Okay, so hopefully it doesn't crash. So, oh, this is a different one, actually. I didn't want this one. I want this one. Here we go. All right, so you'll notice that as we keep going up, and it crashed. All right. Okay, you know what? I think I showed it to you on a website once.
Yeah, you did. I was gonna ask if you could just go to the site where it's at.
All right, let's see if this works. Okay, I think it's over here is where I got it. And it should be like all the way down to the end. This is a great article, by the way.
Nice. Is this
right here.
Is this University of Texas? This is
well, it's actually written by someone at the University of California.
Oh, okay.
His name is like John Bays.
Oh, look at that. That's so crazy. So
yeah,
this approximation is getting very close to the actual number of primes. That's insane. So it's basically just oscillating up and down.
It's back and forth based on what they call like waves that are coming from these non-trivial zeros. There's like a whole side to it where they say like music of the primes, and I know I'm not really into music, so I never got into that kind of stuff.
Yeah,
But the point is, watch, when he goes back to 1, so you start with an initial approximation, right? That almost
yeah.
looks like a straight line. And then
That's so wild. Yeah.
as you add more and more zeros, this function starts to act exactly like the staircase of prime. And in fact, as you approach infinity, it becomes exact, I believe.
Well,
Because,
according
you can
to
also be,
according to Riemann's hypothesis, it becomes exact, right?
yeah,
As long as that's
yeah.
true,
I
which it seems to be.
I mean, if you like, also, I mean, I guess you can think of it like practically. Like, if you're using this to approximate the number of primes less than 100, and say you add 50 zeros and you're at like 25.8, and then you add 50 more, you're at like 25.6, and then you're at like 25.4.3. Like, at a certain point, you're like, okay, I can just stop. It's 25.
Yeah.
But I mean, in terms of putting it all together, yeah, it becomes exact.
That's so wild. That's super cool.
Which is really cool. Yeah.
And I don't know if you know this, but do you remember like what year Riemann was doing all this stuff?
1820 something.
So he was doing all this without computers. This was like so crazy.
Dude, that's when they were more efficient. They had nothing to do.
Yeah, for real.
Yeah, so probably I think 1850s, I'm assuming.
Okay.
I mean, since he's 1826.
Yeah.
But they say that when he passed away, his maybe was it wife? She threw away a bunch of like papers
No
that
way.
he had, like his bunch of his work that was never read. So I'm thinking like, what if the proof to this was in there?
That's so crazy.
Right?
I wonder if those papers are just completely destroyed, or if like they're buried somewhere on planet Earth.
I mean, have you read his original paper?
No.
Like, you can always find it in German or English, and it's like the statement is like, he's like, it's very probable that all the roots are real, but he's like, after many bad attempts, I'm just going to put it away for now, as it seems unnecessary. And I'm like, yeah,
So
it seems very
crazy.
unnecessary to us now.
Yeah.
But
Dude,
maybe you just can't prove it. You never know.
That's crazy. All right, so we're at about an hour, and this is super interesting. We could probably go on for quite a while, but I want to, just for fun, talk about my dream here at the end to end this thing. Because this is semi-related, but not completely related. This is more related to the modular arithmetic part that we were talking about. And we alluded to it, so I feel like I better bring it up again. So, what I was thinking about, I don't know why I woke up thinking about this, but basically if you take 10 squared, you get 100. You add the digits of 100, 1 plus 0 plus 0, and you get 1. And 1 is a perfect square. 11 squared, you get 121. Add the digits, 1 plus 2 plus 1, you get 4. 4 is a perfect square. 12 squared, 144. 1 plus 4 plus 4 is 9. 9 is a perfect square. 13 squared, 169. 1 plus 6 plus 9 is 16. 16 is a perfect square. Okay, so just I'm giving everyone the idea of the pattern. So I woke up oddly squaring numbers in my head just because I'm weird, and I was thinking about that, and the pattern, it's weird because the pattern goes on for a while, and then it'll stop, and then it'll kind of pick up again, and then it'll stop, and then it picks up, but whenever it picks up, it seems to be like these strings of perfect squares, which I was like, there's got to be some reason for this. So I was talking to Hamzah about this, and you were talking about how this is related to modular arithmetic. So I'm now passing it off to you. Do you remember what your solution? You were talking about it being mod.
It was something mod 9.
I think it was mod 9.
It was like, I forget, but do you still have like because I texted it to you.
You did.
Right? Do you still have it?
Literally before I started talking, I was trying to find it, and I was scrolling way back, and I still haven't found it. But
hold on, I can definitely find it because I know I sent you a screenshot of it, and I know it was back in March.
Did you send a screenshot? I was literally going through like all our texts. Trying to find
Hold on,
it.
no, I can definitely find this. Give me like.
Okay. So anyway, as he's trying to find that, I was talking. I was trying. This was in my undergrad years, and I was trying to figure it out, and I couldn't really figure out why that pattern was there. but when I was talking to Hamza, he's like, "Oh, it's related to Mod 9 arithmetic," and basically it's because modular arithmetic is it cycles through, and so that's why you see the
Yeah.
pattern show up every so often. I don't know
So,
if I don't know if we've completely solved it yet, but I think we're like pretty close to figuring out that pattern.
all right. So I found the screenshot that I sent you.
Okay.
And all right. So if a number is a perfect square, then its digit sum must be 1, 4, 7, or 9, mod 9. So 9 and 0 are obviously taken to be equivalent. So for example, 13 squared is 169, 1 plus 6 plus 9 is 16, and 16 mod 9 is 7.
Yep.
So when you're taking all these numbers and squaring them, it actually never fails. When you said 17 would fail, it doesn't, because 17 squared is 289, 2 plus 8 plus 9 is 19, and 19 mod 9 is 1.
Yes, that is true. Yeah. Oh,
Right?
that's right. That's right. So Hamza
Yeah.
was saying the pattern actually doesn't fail when I thought it failed because I wasn't doing mod 9 arithmetic. So
Yeah.
if you add the digits, you get either a perfect square or not a perfect square, but then you do mod 9, it's always a perfect square.
Yeah. So
Um,
you were seeing the pattern because you were squaring all these numbers, and numbers related to 1, 4, or 9 were coming up, which is like most of the time. Right?
Yep.
Because like we said, if a number is a perfect square, then its digit sum is 1, 4, 7, or 9.
Yep.
And what you were doing is you were squaring numbers. Like, you weren't just picking a random number, you were squaring them.
Yep.
Right? So
Yep.
if you so obviously it's not every single number, because if you go in a list and square everything, this will hold. But you can't just pick a number that's not a perfect square.
Yes.
I think that's probably the good way to.
I don't know. I mean, I'd have to think
Right way to put it.
I'd have to think through that a little bit, but I think that's probably true. Like, let me randomly pick 113. 1 plus 1 plus 3 is 5. 5 mod 9 is 5, and that's not a perfect square.
Yeah. But if you square 113, it
yeah.
will hold when you add the digits of that result.
That's so crazy. Okay, so hold on.
Right? So let's square 113.
That's what I'm doing right now on my calculator.
It's 12,769.
769. So let's add those. 15 plus 7 is 22, plus 2 is 24, plus 1 is 25. It's a perfect square. Like, before we even do mod 9.
Before you even do mod 9.
Yeah.
What happens if you take a mod 9? You get 2, right? No, you don't get 2. You get
no, you get 7. No.
You get 7,
Yeah,
right?
7,
yeah, 7. So 1, 4, 7, or 9.
Yeah, that's weird.
Yeah.
Okay. I gotta explore this a little more, but I wanted to end with the weird dream that was related to modular arithmetic.
So now they know about it.
Now they know about it, yeah. Anyway, thank you so much for coming on, Hamza. This was a fascinating talk, and if you guys have any questions about the Riemann hypothesis, feel free to comment below, and myself or Hamza will respond.
And if you have any corrections, I'm sure we messed up on something.
Yeah. Oh, yeah. I'm sure there's any mathematicians out there that want to correct us. I'm sure we did, but it was a fun talk. I enjoyed our time, and we will see you all on the next live stream.